And welcome back. So now that you know about static area, the heap, the stack, how much of that do you have to manage? How much of that does the system manage? Let's actually dig deeper into that. So the heap is dynamic memory. As you saw before, it's a large pool. It's not necessarily contiguous, although every memory request will result in a contiguous region. If I say int, I want 1,000 ints, it's going to give you 1,000 ints contiguously. Then I want another 1,000 ints. That second 1,000 may be very far away or very close to the original, or maybe back to back, maybe abutted, maybe far away. You don't know those things. As you saw before, this is how you call it. You say Malik, the size you want, how many bytes you want, and it returns uninitialized memory. All that's garbage. You then have to initialize it and use it before. You have to write to it before you read from it. You know that before. How do you manage that memory? Well, code and static are easy. They don't grow, and they're managed by the operating system. So don't worry about it. The stack space is also easy. Every time I make a function call, a new frame is created. Every time we return from a function call, that frame goes away and that stack pointer internally moves things around, and you can't get access to that explicitly. There are ways around it if you really know how to do it as a pro, but for the most part, you don't get access to that. You don't control that explicitly. The system does. You'll do when you're writing assembler. You'll actually will explicitly do that, but from the point of view of C, it's below your abstraction line. Managing the heap is tricky though. You don't have to do a lot of memory management in terms of thinking about where to move things around. Again, that's the OS is doing that. But you need to think about the requests, the size of requests you make and how you work with it. So let's actually let's dig a little deeper into that. You want Malik and free to be fast. Stack allocation was really fast. Here, int AR, open square bracket of 1,000,000, boop, really fast. If it works, if it doesn't work, it crashes. But if it works, it's fast, really, so that's great. But you want Malik and free to be fast. You want to memorize memory overhead, how much bookkeeping you need to keep track of to do this. And you want to avoid fragmentation. You probably heard of this with your disk, where you have, one file might be broken up into lots of pieces. And that's an issue, actually, with Malik. And that's probably the biggest issue. So how we deal with fragmentation is the core problem with that. And technically, we call this external fragmentation, because you have these things. There is something called internal fragmentation. We'll talk about that at some other time. So here's an example of what fragmentation looks like. So you put a request R1 for 100 bytes. Boop, there's 100 bytes. Yay, we got our space. Then you make R2 for 1 byte. There's a byte. Then I free R1. Fragmentation. Those two spots are now your memory has been fragmented to two areas. And when you say request R3, where does R3 go? Does it go above? Does it go below? How is it being smart about where to put R3, thinking about what your past pattern has been and what you should do? So this is an interesting question, how you manage this memory, how the system manages memory. You don't have to worry about how the system will manage memory for you. So if you want to read K&R, there's a section 8.7 that talks about some features that we're not going to worry about, but it talks about some idea that each block of memory actually has a header that says the size of the block and a pointer to the next guy, almost like a linked list. Look at that. And it turns out it's a linked list except when you get to the end, in which it wraps around to the beginning again. So it's kind of a continuous circular linked list. It's kind of neat as a data structure. And all the free blocks are kept in there. So initially in the program before, we had this one big area. And once I made a request and then made a second request and freed it, now all of a sudden we call our free list now has two elements in that circular linked list. The top area and the bottom guy are now two of those elements in that circular linked list. Kind of neat. How's Malik work? Well, Malik says, you've given me a request, some size. I have to now search my free list to figure out, can I serve you the memory you wanted? So it looks the free list and it walks the free list. Remember, it's a linked list. Slow, right? All the way around. If none are found, it says sorry, nothing, and it returns null. Okay? So that's important. Free, here's what free does. Here's a free space. Here's a free space. You're freeing the guy in the middle. Well, once you free the guy in the middle, shouldn't this coalesce into one big free space? So free has to do some work. So all of a sudden you realize that Malik is no longer Malik's a function call, right? You're making a function call to Malik. So Malik isn't like instant return. AR of 1,000,000, AR square bracket, close bracket of 1,000,000, that array request is really fast. Like that next line is instant, basically one clock cycle. But Malik could take a long time. First of all, we got the overhead of a function call, which we haven't talked about yet, but there's some overhead to that. And But you need to know, at least you know that the stack has to grow, right? It's a function call. Every function call grows the stack. So Malik has a function, the stack grows just to call Malik. It's kind of funny how the stack and Malik are both, Malik's going to affect the heap, but you got to grow the stack to even call a function, and that Malik is a function. But Malik has to then walk its free list, has to look up its tables and do its stuff and do its internal mechanics to walk its circular list to find out what you've got. And maybe it's a lot of slivers. Wow, you can imagine Malik takes a long time to return null. That's crazy. In fact, that's the worst case, right? It took all the time. You paid the price in terms of clock cycles. Your program kind of stalls out. And then, you won't see it, but I mean, internally, if you were living at the speed of a gigahertz, you'd be like, I'm waiting here. I got some places to go. No time. Goes around, and now I waited all this time, and then even then you didn't give me anything? Really? So that's hard, okay? So how do we choose a spot? As I'm searching, how do I choose a spot? Here's some common ways to do this. So best fit says, I go through everybody. You asked for 100. And I say, of every single free block I have in my circular list, which is closest to 100? If I have 100, done. If the first guy I was looking at was 100, done. Here's the 100. But if I have 101, well, maybe I keep looking to find 100, okay? You can imagine that's a little, I could have given the 101, but who knows if I would have had a perfect fit later. It's almost like you're trying on a clothes. It's not perfect, but kind of a little long here, a little long there. No, I want the perfect fit. Best fit says I gotta have search everybody to get that. You can see the trade-offs there. But I will give you exactly the tightest fit I can. Now, what if I had a gap of 104 and you asked for 100? Well, I now have a sliver of 4. See that sliver? They're going to start to accumulate. So think about that. These slivers become now, that sliver is still another element of my list. Now I used to have 100, now I have a little sliver of only 4. And so you might have a lot of these slivers that make my list even bigger. Oy, oy, oy. First fit says, all right, I come into the list, I grab the first guy I can, fast as I can, get in, get out. Boop, anybody bigger than 100? Nope, nope, yes, bigger than 100, yours, go. As I start to use that, you might need to see a lot of these slivers start to happen at the beginning. Right? There's always a pointer to the beginning of the circular list. Well, you can imagine the slivers might start to grow in the front. Now I have a lot of these slivers in the front if I keep doing first fit. There's a lot of action in there, making a lot of pebbles. If you think about getting from here to the deep ocean, the pebbles are there, like as you walk through the pebbles to get to the big rocks down low. Next fit says, it's like first fit. First one that fits, except that rather than always start from the beginning, it rotates. Wherever I stopped last time, I'll remember that, and that's the next time I'll do it. So next fit says, remember where you were, and go through, that's where I'll start next time. So then I'll do that. So it kind of distributes the pebbles, if you think about that, around that, and that's kind of interesting. Resume searching from where you stopped last time. And there are trade-offs on all three of them, and you can think of workloads that may make each one of those three look really good or really bad. You can think of that as well. In conclusion, this is the semi-final lecture in C. Very exciting. We're almost at the end. C has 3 pools of memory: static storage, the stack, the heap. Static doesn't move. The stack grows and shrinks with function calls, and it's where your temporary variables are and your parameters. And the heap is where your malloc action happens. Okay, that free and malloc action happens. 3 ways to deal with the free list that malloc's going to affect. Best fit, find the one that search everybody until you find the one that just snugly fits the best. First fit, always start at the beginning. The first guy that matches, that's bigger, that's equal to or bigger than the space you're asking for. And and next fit says the same as first, except that you always remember where you were and start there next time. See you at the next lecture. We're almost there, folks. Take it there.